All right, so let's talk about the squeeze theorem, theorem 1.8. So just FYI, to my knowledge, the kind of homework questions you have, you're not going to be asked to use the squeeze theorem directly just yet. We will definitely need to have practice with them because it's definitely a contender on the free response portion of the exam. Um, however, for us right now, we're going to be introduced to the squeeze theorem, but in reality, how we're going to be using the squeeze theorem is the squeeze theorem allows us to come up with these three special limits that you see here. Why is my pen not working? Okay, so these three special limits. So currently in our textbook, you're being introduced to the squeeze theorem because they help prove these three special limits, which you're going to now use to find limits of trigonometric functions or limits involving trigonometric functions. Okay, so I don't want you to be all confused, like why do we go over squeeze theorem and then I don't see squeeze theorem questions. Well, there it's kind of like embedded in there. Okay, but let's get a good introduction to it. So here we go. If h of x is less than or equal to f of x, which is less than or equal to g of x for all x in an open interval containing c, except possibly at c itself. So really quick before I read the rest of it. So we have a situation where we have three functions, and if we just set f of x to be the middle guy, we know that we have a lower limit, which is h of x. So we know that h of x is always going to be less than f of x or equal to it, right? It's never going to be greater. Same idea here. We have another function called g of x, which is always greater than f of x or equal to it, but it's never going to be less than f of x. And we have this situation represented graphically here. So as you can see, g is always above f, which is above h. H is always below f, which is below g, except possibly at c itself. Now, even though c is undefined, it doesn't matter because we're talking limits, guys. So let's read on the next part. And if the limit of h of x as x approaches c is L, which is also equivalent to the limit of g of x as x approaches c. So notice these are my lower and upper caps. And as we take the limit as x approaches c, we find that their limits are identical. Then the limit of f of x, or the limit of f of x as x approaches c not only exists, but we know that it's equal to L. So let me try this analogy here. So let's say we have a person A that says, I'm 6 foot. I know a person B who is taller or the same height as me. Either my friend B is either going to be taller than me or going to be the same height as me. Then we have another guy here who is person C, and this person is also 6 foot. But he makes a claim, my friend B is either shorter or the same height as me. Now, if I were to tell you that person A and person C are telling the truth, what can you conclude about the height of person B? You can't be greater than 6 and less than 6 at the same time. You have to be equal to 6. So we know that person B is also 6 foot. So maybe the informal nickname for the squeeze theorem might better represent this idea. The squeeze theorem is also called the sandwich theorem. Yum, yum. Hope you're not hungry. Okay, so now I'm going to go through and take you in proving theorem number 1. I hope you can see how you can also derive theorem number 2 and 3. It's not necessary for you to know the proof, but we do definitely need to see an illustration of the squeeze theorem, and that will also hopefully be helpful as you use these limits later on. Okay, so before we go to example 9, I'm going to show you how to prove the very first theorem. And to do that, I'm going to have to take you back to pre-calculus. Let's go to the unit circle. So here we go. So I got a little board ready for you. So hopefully you recognize this as a unit circle. It's a unit circle because the radius is 1. And what I did was I drew a triangle here. Notice it extends beyond the unit circle, okay? So I just redrew that triangle right over here. And let's just name these parts. Because this is a unit circle, we know that this length here is just 1. I don't know what this guy is, so let's just use the notation for right triangles. That's a hypotenuse, I'll call that C. Based on the way I drew my drawing, I like to make A the smallest and B the middle, so I'm just going to call that B. Now then, what I want to do is I want to play around with this 1, B, and C, because I don't think that's going to be very helpful. Not just yet. So what I want to do is introduce some trig ratios here. So why don't we try and take the and we can do this for sine, cosine, and tangent, but you'll see I'm only gonna solve for the parts that we need. What I want you guys to do is follow me and find the tangent. Tangent is opposite over adjacent, which in this case would be b over 1. Therefore, how can I rename tangent, or b is just tangent of theta. So now I can say that this height, right, or this vertical distance is tangent theta. In other words, I have just found the coordinates of this point right here, which is 1 comma tangent theta. Okay. So now what I want you guys to do is consider the area of this triangle. The area of a triangle is 1/2 base times height, and based on the way I drew my triangle, it should be 1/2 times b, which is in our case base length of 1, times height, which in our case is tangent theta. So now we know that we have this right triangle that we created from the unit circle, and the area of the right triangle would be 1/2 tangent theta. All right. So remember, we're working with the squeeze theorem. So if you haven't realized, we're gonna need 2 more triangles. Okay. I wonder if this is the biggest one. I wonder if this is the smallest one. Oh, actually, one of them is gonna be a sector. So the second one that we're gonna look at is the sector. Notice the commonality between all of these is that they're going to share the same reference angle, right? So let's take a look here. Oh, I should maximize. Oh, no, but when I do that, I can't change colors. Oh, right now it's okay. All right, so let me just redraw that sector over here. It's not going to be very nice. Eee. Forgive me. It's like a little trig pizza. Anyways, to refresh your memory, the area of a sector is simply, when the angle is in radians, 1/2 theta r squared. For us, this is pretty easy because we know that the unit circle radius is 1. Therefore, we know that the area is simply 1/2 theta. And finally, we're going to have our smallest triangle. I'm going to have to zoom in a little bit on this. So I'm going to trace it in green. And as you can see, the area is slightly less than the area of the sector, even visually speaking. Okay. So for us to find the area of that triangle, what we can do is simply find the height, because we already know that the base is 1. So to find the height, we might want to create a right triangle, and the height we'll just call h. Now another interesting thing about this triangle is we know that this length of the triangle, or the leg of the triangle, is also 1, because that's part of the radius of the unit circle. So if I want to use theta, this h is opposite hypotenuse, that's going to give us sine of theta equals h over 1. So h is just sine of theta. Therefore, the area of this triangle is 1/2 base times height. So what we have right now is a situation which is very similar to what we saw in the squeeze theorem. Okay. And I hope, even visually speaking, we can confidently make this statement. All right, so let's take a look. I'm going to write down the areas of each of these little triangles and sectors. I am going to write them a little bit differently from how... So for example, for the red, our largest triangle, instead of writing it as 1/2 times tangent theta, I'm going to write it simply as tangent, oops, let me change the color on that. We'll say tangent theta over 2. For the blue, we found that it's theta over 2. And finally, for the green, we found that it's sine theta over 2. So now when we multiply each expression by 2 over sine theta, something fun's going to happen. And the reason why we do this is because it's legal. It's legal math. We're not changing this inequality. As long as I treat each part exactly the same. So for the first, you see how they're reciprocal, so you'll get a 1. For the second, the 2's will disappear, become 1. So we have theta over sine theta. And let me do a little bit of side work here. Notice initially we're going to get tangent theta over sine theta. Well, tangent theta is really sine theta over cosine theta, and that's being divided by sine theta. Losing the division sign, we need to add the multiplication. However, we take the reciprocal, so we really get 1 over cosine theta. All right, so things are looking good. Now remember, this is an example where we're illustrating the squeeze theorem, right? So that means we're somehow going to match up these ends. Right now, when you look at 1 and 1 over cosine theta, that should really have no meaning, right? 1 over cosine theta, maybe some of you guys are thinking secant, but that's not really much of a connection. However, if you remember the special limit that we are trying to prove, we want to know as x approaches 0 for sine x over x, right? That the limit of sine x over x as x approaches 0 is 1. We already know that this is going to happen. So as we're proving, maybe we can refer back to our final destination to kind of give us a preview of what to expect. So we already have this 1 here. That means somehow we need to show that as theta in our case, notice our variable is theta instead of x. As theta approaches 0, how can I show that this quantity will also approach 1? 1 over cosine theta or secant is not really a trig function that a lot of us are super comfortable with. So why don't we use a little bit of algebra to turn it into something that we can work with, which is cosine. Because we're pretty comfortable with cosine. We're pretty comfortable with the unit circle, right? So what we can do is basically take the reciprocal of each aspect of this inequality. So before I do that, I want to do a quick illustration. So let's say we have the inequality, the fact that 1 is less than or equal to 3. Now what happens when I take the reciprocal of each number? 1 stays a 1, but the 3 will now become a 1/3. So what would I have to do to adjust to this new situation? I need to reverse, flip the inequality sign. So when I do the same here, the reciprocal of 1 is 1. The reciprocal of theta over sine theta is sine theta over theta. And finally, the reciprocal of 1 over cosine theta is simply cosine theta. I can no longer use the same inequality symbols. I need to flip them. Now that I have made the statement, I can attach the limit notation and basically take the limit of each part as theta approaches 0. Well, let's work with the left side. We know that 1 is just going to be 1 no matter what. It's unaffected by theta. So the limit as theta approaches 0 for 1 is just 1. Then let's take a look at this guy right here. We see that the limit of cosine theta as theta approaches 0, think back to the unit circle. What's happening? You're approaching the positive value 1. And if I just leave my middle term as a limit, I think it's going to make it very clear. So now I can make the statement by squeeze theorem, the limit of sine theta over theta as theta approaches 0 is equal to 1. Now I do want to keep in mind that something that I did a little bit indirectly, I did make it really clear that I had 3 separate functions, right? I have my, in our case, so let me write that really quick. H of x is less than or equal to f of x, which is less than or equal to g of x. So in our case, h of x was the smallest area. F of x was our middle. And our tallest was like that. All right, now good luck. Let's move on to the example. All right, example 9, a limit involving a trigonometric function. Find the limit of tangent x all over x as the limit of tangent x over x as x approaches 0. Alrighty, so first things first, let's attempt, and time to change my color. Let's attempt direct substitution. Let's do the easy one first. So that's already a no-no, right? We can't have a 0 in the denominator. Now, what about tangent x? Maybe it'll be more helpful if we rewrote it as sine x over cosine x. So what is sine of 0? It is 0. Cosine of 0 is 1. So it's 0. So once again, we have an indeterminate form. Alrighty. Okay, so in order for us to work this out, start with the new space. Let's define our function. And in fact, what I want to do is separate the sine and cosine from the tangent. So maybe I will write it like this first. So that's our tangent times 1 over x. So I'm just going to rearrange things a little bit and write it as sine x over x. Oops, not equals, times 1 over cosine x. All right, now as you can see, we have a product. So using our limit properties, let's separate these out. So let me first write it out. Oops. So let's start from our initial. So now we redefined it as sine x over x times 1 over cosine x. And using our limit properties that we learned earlier, we can write times the other. Okay, so let's do a little bit more color coordination. Let's take our first bit, and here we go. As you can see, we can match it up right there, right away. So that just becomes 1. Then what do we have for the limit of 1 over cosine of x as x approaches 0? Maybe we want to do a little side work here. Once again, separate out the numerator from the denominator. The limit of 1, no matter what x value it is just going to be 1. The limit of cosine as x approaches 0 is going to be 1. And so we also have 1. Our final answer is 1. So when you have a limit involving a trig function as of right now, what you're going to do is try to locate one of the 3 special limits. Okay? That's the strategy. You're going to try to look for one of these 3. So let's do one more. A limit involving a trigonometric function. So, I mean, just by looking at this already, I hope you're already thinking, yeah, that looks like we're going to use number 1, right? That almost looks exactly the same. However, how is it different? It's a little bit different, right? Because it would be perfect if we can have sine of x over x, but the problem is we have a big fat 4 over here. All right. So what if, so if you have an issue like this where you see, I feel like I can match that up pretty well, but the sine of 4x and the x are not matching up. But notice all I would have to do really to match this up was if there was a 4 there, right? Isn't that kind of like if I let u equal 4x, wouldn't that basically be, so maybe I won't write the limit notation just yet, because then it doesn't really make sense. But it's like sine u over u. And that should fit pretty well with that, right? Okay, so we want it to be the same. So is there a way we can get away with multiplying a 4 in the denominator? Can I just multiply it by 1/4? No, but I can multiply it by 4 over 4. Can't I? Yeah. So what happens here? I can rewrite this as the limit as x approaches 0 of 4 times sine of 4x all over 4x. Now that I have a scalar, even though I could just factor out the entire 4 over 4, then there's no point in what we did, right? I'm just going to remove the 4. And what I hope you guys understand is now I've created a situation where I can apply our special limit. But there's still this one problem, okay? We know that we can't use 4x and 4x because, as you can see, the special limit requires x, x, and x. So they need to be all the same variable, right? So why don't we use what we used before and say u is equal to 4x. Then as x approaches 0, what would happen to u? As x became smaller and smaller, or bigger and bigger from the negative side, it's still going to approach 0. So now I can rewrite using a different variable. So it's a little bit easier for us to match up with our special limit here. Okay, so the only difference is I've replaced all the x's with u's. And I can simply say it's 4 times 1, which is 4. All right, good luck.